Yeah, yeah. I think we have a quorum now. We can start. Professor Colpi, please take over.
Okay. Good morning, and again, namaste. This is my last lecture, and here is the outline. I will mention 3G detectors, so the next generation of detectors, Cosmic Explorer, but in particular Einstein Telescope, because it is a European experiment. But I think that we have to consider that we will have a global network of next generation detectors, and we will always work together, especially to localize the source. So in the future, I think it is really bright, because we will have all over our Earth planet detectors to sense our beautiful universe. And then I will move to LISA, which is the laser interferometer space antenna. So it is our interferometers, the first in space. Let me mention that a similar project is also planned from the Chinese Science Academy, and maybe we will have 2 LISAs around. Taiji and Tianjian are the names. And I will describe first LISA sources, and then I will explore a topic that it is extremely important for me, which is the synergy that you can do with LISA and third generation gravitational wave detectors, not only to study neutron stars and black holes, but to really understand whether there is a fil rouge, that is a deep connection between stellar and supermassive black holes. This is a topic I'm working. And here in this slide, I have shown two Nature physics reviews. The first is an overview of what will be the gravitational wave physics and astronomy in the next decade. So also included in this review, there is also the pulsar timing array experiment that I didn't describe, and I will not describe because I don't have time. And the second is again a Nature review paper on the origins of supermassive black holes that I wrote together with Marta Volonteri and Melanie Habouzi. It is broader, but it is really addressing the connection between LISA and ET. To answer a question that for astronomers is really becoming not only interesting but very urgent to discuss. So let us start with the third generation detector on ground, and again here for your references, we wrote the science book, and also if you browsed in the web, there is also the book on the specification of the shape and how will detector will be constructed. In general, in US, Cosmic Explorer will be on ground and extended up to 40 kilometers, the arm length. And instead, Einstein Telescope is a cryogenic underground detector. Then there is a lot of still discussion in Europe, both on the shape or in the location. But what we know already today are the planned sensitivities that will guarantee a stepsize increase in sensitivity. So let me just show here the strain noise, so the sensitivity expected by these interferometers as a function of the frequency. So here, please notice the frequency range. It is extending from 3 Hertz. Currently, you see that the sensitivity curves in the advanced configuration by LIGO has a very sort of becomes highly insensitive at frequencies below 10 Hertz because of Newtonian noise on Earth, and it can be extended up to, say, 4,000 Hertz. So if this is the advanced LIGO sensitivity curve with the third generation gravitational wave detectors, we have an increase in sensitivity by more than 1 order of magnitude. And also, since especially Einstein telescope will contain a high frequency and a low frequency interferometers, the green is the expected sensitivity by Einstein telescope, and the purple one is by Cosmic Explorer, that is the US interferometer. The very solid line in all three curves is represented the optimal sensitivity, whereas when you so the strip is showing the median and the 10 best percent sources. So the median is here, and here is showing the 10 best 10% sources. If you extend to lower frequencies, let me remind you, and I will repeat again, that we see highly redshifted sources, because remember, the frequency in the detector frame is redshifted by the expansion of the universe. And so if you are increasing the sensitivity below 10 Hertz, we can go deeper in redshift and also have the possibility of discovering the most massive stellar origin black holes. When we move the sensitivity to very high frequencies, as I will show in a moment, we can have the chance of really detecting the merger and ring down of the relic of the merger of two neutron stars. And always, we always have to remember that we might really also detect sources for which we do not know the origin and that we never even thought in our mind. Normally, given a sensitivity curve, you can construct two plots that carry the same information. This is this is what is usually done in the books on ground-based detector, and then I will show also how we do in when we use low frequency detectors like LISA. Here again, I'm showing a plot which is amazing because it is showing the total source frame mass. So this is the binary mass. So we are always talking of coalescing objects, and here is the redshift in logarithmic scale. This curve here is showing the horizon of advanced LIGO, so with the same colors of the previous figure. And when we plot the horizon, we show the theoretical limit, because for a given mass, let's say 100 solar masses, we can read this plot showing that we are sensitive to sources that are around redshift 1.5. And to see this source with this mass at this redshift, the source has to be just in the best position in the sky, so orthogonal to the plane of the interferometer to have the highest sensitivity. Then if you just consider the first shaded area, this is comprising the expected 10% of the sources, and the other area is indicating that around this area we are detecting the 70% of the sources. I have plotted here the redshift of what we called in the first lecture the high noon, that is redshift 2, when we witness the peak of the star formation rate, which is also the peak of the formation of the relic stars. Then at redshift 7, 8, we have the reionization of the universe, and the dark ages end around redshift 20 or 30. So in between, during cosmic dawn, let me remind you, the first stars from primeval gas are forming. And then you see that the sensitivity of Einstein telescope and Cosmic Explorer is incredibly enhanced. So the horizon, so the theoretical limit is about 100, where we don't know whether there might be primordial black holes merging, because we know that stars are unlikely to form at this redshift. And so we can probe a star formation, exotic star formation, in a domain that is not accessible by any electromagnetic facility. So since we know that neutron stars exist in nature up to a maximum mass of around 2 solar masses, please notice that we can detect neutron stars up to the peak of the star formation rate, but for the black holes is the entire universe. And also please notice that we can extend in the source res frame the mass interval up to 10 to the 4, or let me say up to a few thousand solar masses. So we are exploring the so-called intermediate mass range for black holes, that, as I will explain, is extremely important to know if they exist and if they are just the parent population, or, as we say, the seeds upon which supermassive black hole had formed. So we, when we were writing the science book for the third generation gravitational wave detector with Vicky Calogera, we decided to use 3 adjectives to impress the people about the possibility, the potential and the performance of 3G detectors. We are going to be deeper because we are going to dig deep into the cosmic, the early cosmic ages. We go wider because we are extending the frequency spectrum, and we go sharper because some source will be extremely bright. This is again the same plot, but we changed 2 things. We have plotted the redshift in linear scale and not anymore in log scale. Again, the x-axis is unchanged, but here these lines are so-called lines on constant signal-to-noise ratio. So there is an additional information, and as a rule, we know that we can detect a source every time it has an SNR larger than 10. And when we do this plot, we have to also decide which is the mass ratio because of the binary, because the mass ratio is entering the amplitude of the waveform, and the smaller is the mass ratio, the weaker is the gravitational wave amplitude, and here is for mass ratio 1, so for the loudest sources. And we don't know whether we have a 1000, so a 500 plus 500 solar mass black hole, or we have a 1000 solar mass plus a 10 solar mass. So the ratio would be larger, and so or smaller, whatever you define, and so the sensitivity would be less. The message here is that, again, we are covering the entire universe, and but you see that in the nearby universe, with the sensitivity of this instrument, we can detect black holes up to this mass range, but with a signal-to-noise ratio of 200. So these are really very loud sources. So we can really extract from the signal the information which can be accurate, very, very accurate, as I will show in a moment. And instead, if you combine not only Einstein telescope, but two cosmic explorers, wherever in the United States, or, then you further increase the sensitivity, and notice how larger is the enlarged is the sensitivity band in mass. Here we are far sensitive out of redshift to the recombination between 30 and several hundred, here below 10 up to almost 1000 solar masses. So it is really amazing how the science that will come out from Einstein Explorer and from the network. Let me go back here that I didn't read this, these two numbers that are quoted. Per year, with the 3G detectors, we are going, or we expect to see 10 to the 4 up to 10 to the 5 neutron star merger per year, and even 1 million black hole detections per year. So you can imagine that we know we see 100 millions of galaxies in survey, and as well as we know more than 1 million of quasars. I think I'm quoting right these numbers. And in a year, you can see all the black hole, already 1 million. And so since 3G the terrestrial detection can be long-lived, the knowledge at statistical level would be huge, but also you understand that it is also a data challenge, because you will have many, many events every day that you have to study. And so it's a lot of work in analyzing the data. Concerning neutron stars, having enlarged the frequency band beyond 1000 Hertz, the beauty of this is that if your sensitivity is becoming worse around 1000 Hertz, let me just go back here. Well, this LIGO, advanced LIGO will do okay, but not yet at present. So here you have the beauty. Here what I'm showing again the sensitivity curves of initial LIGO, of advanced LIGO that we expect in 05, and Einstein telescope. And this is the typical signal in the frequency domain, here I have the frequency of the gravitational wave on ground. We have a neutron star at a 100 megaparsec, and with advanced LIGO, but especially with Einstein's telescope, we can start measuring with accuracy the tidal effects that are imprinted in the waveform, and not only that, but also the richness of the frequencies which are associated to the oscillation of the newly born and highly deformed neutron star. This is one example that I think I got from a paper by Rezzolla, that if you have a neutron star, it's not like a black hole that you have the ring down, which is decaying with a precise number of frequencies or quasi-normal modes. Here you see that you can extract many, many frequencies. And so you can really learn about the deep interior of a neutron star if not a black hole, but a neutron star has formed, even temporarily. So if you have two light neutron stars, the relic is a first differentially rotating neutron star, then you have uniform rotation, then it might, due to the loss of rotational energy, might become a black hole, but you see the features that are extraordinary. And I just added before just added today. This is the signal of GW, so the heavy black hole that it is in the pair instability gap. And so you imagine you have instead a 10 solar mass or 30 solar mass black hole at redshift 10. The frequency is, the mass is redshifted, and it would appear as a 30, as 300 solar masses. So you see only few cycles. So as you move to high redshift, you see less and less cycles from the merger of two black holes, but then you can extract that information and discover the very first black holes. So I think I have convinced you that with the third generation gravitational wave detector, we will discover stellar black holes through cosmic ages, from cosmic dawn to the present. We might also discover, which is a very hot topic, also the existence, if they are, of what are called the primordial black holes that are believed to form before the first stars are forming. So in this region of the redshift space, they form, so beyond 30. So here is stellar POP3 stars. I should have written, sorry, here I expect to see the POP3, so in this range here, the primordial black holes, for which also the mass can be one solar mass. And so always never forget that if in the gravitational wave signal you have component masses of one solar mass, I think it is reasonable to always to believe that it is a system with two neutron stars. But if you see a system of 0.9 solar masses, it is unlikely that neutron star has this mass, though theoretically it is possible because they form in the collapse of an iron core. And so we might discover these primordial black holes that can carry a very different, a wide range of masses that are inconsistent with being neutron star if below one solar mass. So we can recover the history of star formation, and we can discover the so-called intermediate mass black hole. So it is very, very exciting. Three more considerations that were in principle worth hours of lectures. that I sort of skipped in mentioning, but probably you heard from the previous lectures. You know, and I said in the early lecture that one of the most unique properties of binary mergers of compact objects is that you have the information of the luminosity distance, which is embedded in the signal, but you do not have any information on the redshift. This is contrary sort of to the electromagnetic counterparts. For a galaxy or for a star, it's very easy to measure the redshift through atomic line emission, which we know very well. But to measure the luminosity distance, we need to know, to have established the so-called distant ladder that goes from C fades to type 1a supernovae. And so there are systematic uncertainties. Instead, here we have a good measurement of the luminosity distance, which is degenerate with inclination. But if we measure the polarization of the wave, we have a good measurement of the luminosity distance. And so if we see a counterpart, so like we have seen for 170817, that we see the kilonova, we saw the gamma ray burst and the kilonova, we can then measure the redshift of the galaxy host. And this was a groundbreaking, no, not a groundbreaking, a very important application showing the power of gravitational wave, because with gravity alone, so without using the cosmic distant ladder, so skipping a step that is introducing systematic error, we measured the Hubble constant with a precision which is far larger than the one that is measured by Planck and by type 1 supernovae, but it is the first example that in the years to come, the gravitational wave signals are a way to measure the expansion of the universe. And if, since we said that we will see 10 to the 4 neutron-star merger per year, and not all will have an electromagnetic counterpart, but you need only 100 of these sources that we call standard sirens to measure the Hubble constant at the level, at 1% level, allowing to arbitrate the current tension between the late and early university probe that you might have heard, because Planck data give a value of the H0 which differs from the one of the local universe, and we don't know if this difference is associated to some new physics related to the way we are interpreting the expansion of the universe. But in a seminal paper that I should have quoted, but it is very famous, but by Bernard Schutz in a Nature paper in 80-something, noticed that since the binaries are indeed containing the information of the luminosity distance that has this mathematical expression, if you and are dark, so you don't have any electromagnetic counterpart, but you do not know the redshift, but you have many sources, and this will be the case for third generation detectors, you can use statistical method to infer the cosmological parameters, in the sense that for a given source, you know the luminosity distance, you know approximately the redshift using a cosmology, but then, and you have many host galaxies that can host this source. And so you attribute to each source a redshift with an error. But when you have 1,000 of sources, all the error on the redshift that each source is carrying can be reduced because we are living in a unique universe. And so they sort of should align, should be consistent. And in this way, we can again measure not only the Hubble constant, but also maybe the contribution from the dark energy sector. And this could also be done with the bright sirens if you have very precise measurement of the redshift. So you do cosmology, or more than cosmology, let me say, really cosmography, because we can really learn about the expansion of the universe. So it is a fantastic new field. It is not my field, but I'm always fascinated when I listen to my colleagues, and I am fully aware of the potential. And when we say that we want to develop statistical methods, it means that it is a topic which is associated to the multi-messenger astrophysics, because every time we see a single source, we have to make a big effort in trying to see whether we localize the source to identify the host galaxy. So it is a joint adventure with the next generation of electromagnetic facilities. As I've shown here, the signal-to-noise ratio of nearby sources can be extremely large. And this implies that we can really carry on very accurate measurements on the structure of what we call black holes that can exist also in alternative theories of gravities, as you have seen in your previous lecture. So we can test gravity in vacuum dynamical space-time, or maybe around dark matter clouds. But when you have a source with a signal-to-noise ratio in the hundreds, and particularly in LISA, it can be even larger. So for the massive sources, we can expect during the spiral, during the chirp, to measure post-Newtonian coefficients or deviations from that with a precision which is far better than the current one of 10%. And so with Einstein telecos, we can reach sub% and sub-per-mil accuracy in the search of deviation from GR. And so we might be dominated by by systematic error, which are related to our ignorance in the way we model a waveform, but it is nature that will detect the waveform, and so and not our theoretical waveform. So that would be fantastic, since we can see the ring down in with a very high SNR. So the portion of the ring down with a higher SNR, we can reveal the properties of black hole horizons to measure both the quasi-normal modes and the damping time, to measure the multiple moments of the black hole, whether they are Kerr or not, and for the neutron star, the elasticity, the quadrupole, the deformation of the relic neutron stars. Measuring the spectrum of frequencies and damping times, again, in the ring down for about 50 sources, already in between, in the next 04, 05 runs, even before Einstein telescope, we might still confirm or disprove the Noether theorem. So, which is stating that a Kerr black hole is uniquely identified by the mass and the spin. And so this will be also fantastic. And maybe this will occur before the third generation of ground-based detectors. LISA can do the same. So can do the same, not with black hole of say 10 or 30 solar masses, but with black hole of 10 to the 6 solar masses. So it will be complementary, and maybe the objects that are massive inside the galaxy, might not be black holes, might be boson star or whatever. And so we should expect really new physics. Well, this is already what I said, but I just repeat that if primordial black holes are, we know that they cannot be, cannot account fully. This is what I learned reading the literature. They cannot account fully for 100% of the dark matter, but in this mass range, they could give a contribution. And so we might detect this primordial black hole with third generation. Primordial black hole that are seeded either during the QCD quark-hadron phase transition, but at any phase transition during the radiation-dominated universe, we might form from high density fluctuation this primordial black hole out of redshift trend that are forming at this redshift with a mass which is associated to the specific phase transition. So I think it is something that I really envy you, because I won't see this, but because I'm too old, and so that you are the people that are really be the shaping the science, and so please really be very conscious that you have as an extraordinary opportunity to see a universe that I will never see. And so it's fantastic, but humanity will understand. With both Lisa and Einstein, we could see whether there exist exotic boson stars that I studied when I was young, that are tidally deformable stars which has a surface and could sort of be black hole mimickers, and then see deviation from the kernels. This is again a summary, but I already said this. So maybe I stop here because to answer a question, because now I'm moving to Lisa. And so if you have questions, it's the right time to ask.
Okay. So indeed, there is a question in the chat. So the question is, can you shed light on disentangling lots of sources in particular sky patch while using statistical methods?
Can we disentangle sources?
Yeah, so can you say something about disentangling a lot of sources in a particular sky patch while
yes,
we use statistical methods? Yeah.
Yes, I think it is that it hasn't started yet. We would like also to do in Milano. We hope to succeed. It is the challenge of the Einstein Telescope and Cosmic Explorer. We need to do this, okay? So let me tell you one thing that I am understanding. If you see so many sources, 10 to the 6 sources per year, I think that I never see a paper, but it could be done also almost easily. Let me say this. The black hole coalescences, as well as neutron star coalescences, are transient gravitational wave sources, which means that they stay in the interferometer for seconds or minutes. So over a day, you might expect to see many signals, but separated, not overlapping on average, okay? And so you don't need, so you have to prepare to disentangle two simultaneous sources, but in the gravitational wave data analysis, probably you need to develop very fast pipeline that are detecting the source in low latency, and then you go deeper and deeper in doing the parameter estimation. The difficulties, which is related to the question you are asking, is are we able to alert the people to find the counterpart? For neutron stars, I think that the community has 15 years to understand how to launch target of opportunity searches with alert times that can be minutes to hours in order to see. And this is the challenge of the multi-messenger astrophysics. And then when you go deeper and deeper, you see many galaxies. In 1 square degree, you might have 10 to the 4 galaxies, and you even in your redshift beam. And then I think that we have to understand better the hosts. And so this is enormous amount of work that it is combining knowledge across the fields, data analysis, alerts, and so it is a challenge that we have to face, and we have to start now. And also with LISA the same. And I may comment this later on when I showed LISA. I think there is a second.
Right. Okay. Yeah, Sasha.
Hi. So my question is regarding primordial black holes that you've been referring to a few times on the slides. I was just wondering if there is any clear way to distinguish the provenance of a binary black hole merger, whether the black holes came from stellar collapse or whether they came from a primordial origin.
No, there is.
Oh, I was just going to ask if is the only reasoning that anything beyond a certain redshift has to be of primordial origin? Is that the argument?
The argument is this, and I remember a recent paper showing that it's not so obvious that when you have a source, a redshift 30, and so you are sensitive to black holes in between 5 and 10 solar masses, or slightly more, or even slightly more. Your parameter estimation is so good that you can pin down, given a cosmology, you can say, this is a binary at redshift 30. So you won't be able, unless, at least to our knowledge today, to say this is a binary at redshift 30 of 10 solar masses, or a binary at redshift 10 of 30 solar masses. So it will be very difficult, but the distinction could be the redshift. The other distinction is that instead you go to low redshift and you discover an event. Let me just to give the idea, and I'm just inventing, but it is the correct line of reasoning. Suppose you have a signal that it is involving a light binary, so of around 1 solar mass, and you don't see tidal effects, nor these features. Then the only chance is that it is a black hole in a mass range typical of neutron stars, or even less. But we know that neutron star can exist from 0.1 and the maximum mass of a neutron star. but nature so how to form a neutron star of 0.5 solar masses? There is no theory for this. And so you would be led to say, if I don't see any tidal effect and the black holes are all Kerr and the masses of the component of the binary is 0.5, then it has to be a black hole at low red, a primordial black hole that of a binary that merge at very low redshifts. And so this would also be a groundbreaking discovery if you don't see any tidal effect in a nearby source with the right mass.
I see.
But that would be also very, very, very interesting.
Right. So what I'm understanding is that if you were to detect something that is subsolar, then there is a stronger confidence, and say you don't see any tidal effects, then we have a stronger confidence that this could be primordial. But if you see black holes that are significantly higher in terms of solar masses, much greater than 1, then it's much harder to say because constraining the redshift for these systems is hard.
Exactly. Perfect summary. And primordial black hole can also have very large masses, but then there is a probability that among 1 million black hole binaries, some could also be primordial, but you can't tell, except that you might say, among these, the rate is dominated by the stellar, and there is a fraction that it is primordial. But then you don't know how to choose if they have the masses similar to the stellar black hole masses. So you will never know. You will never know. So this is, your summary is really catching the problem.
Okay, thank you very much.
Thank you very much for your question.
Okay, thanks, Ashwat. Are there any other questions? Okay, so it seems there are no other questions, Professor Colpi. We can maybe move ahead.
And when we go ahead, now it's time to talk about the supermassive black holes, the ones that are at the centers of most of the galaxies of our universe. And except for the very famous image by the Event Horizon Telescope, which in a sense is already telling us the light bending around this very massive black hole in M87 is consistent with a sort of an object which is a black hole, but really you can't say whether it is a Kerr black hole, which means that you have measured the quadrupole moment, so it's still uncertain, but it was a certainly impressive discovery, as well as the discovery of the black hole at the galactic center. This is the Nobel Prize by Gensel, Getz, and Penrose. The stars are still at 1 astronomical unit, and so we start seeing precessional effects in the orbits, Schwarzschild precession, length-theorem precession in the orbit, and the redshift, the gravitational redshift of the light has been measured. And we know that there is a black hole of 4 × 10⁶ billion solar masses. Here instead we have a black hole of 10⁹ solar masses. A black hole, or say a black hole candidate, because only gravitational wave analysis of the signals coming from these will tell us really if they occur or not. LISA is the laser interferometer space antenna. Just 1 minute for describing the interferometer in space. We need to go in space because we need to have longer wave arm length in order to detect wavelengths that are of the sizes of the length of the arm. So frequencies around 10 to the minus 3 hertz, and so wavelengths that are millions of kilometers long. So we have to go in the space, which is very quiet, but of course it is challenging because we have to test technology on Earth and then control in space. It is always a big challenge. But the idea is very simple because gravity is everywhere in the universe. And so we have free-falling test masses in space. On Earth, instead, we have to suspend our mirrors because we have gravity. Here we have free-falling test masses, and we know that the passage of the wave is inducing the stretching and squeezing of the test masses. And so we can measure the stretching and squeezing, that is the proper distance of the test masses, but using light as a way to measure the stretching and squeezing. Let me just, in technical language, these 3 spacecraft which are hosting free-falling test masses, this constellation is the equivalent to the transverse traceless gauge in which we describe wavelength and amplitude, gravitational wave amplitude. So LISA is a constellation of 3 drag-free spacecraft that are at the corner of this equilateral triangle with arm length 2.5 million kilometers long. Since we really want to have free-falling test masses protected by these spacecraft, we have to find an orbit in free space. And so LISA is on a trailing heliocentric orbit between 50 to 65 million kilometers away from Earth, with a baseline which is comparable to, which is the two astronomical units. So it is really orbiting around the sun as Earth is orbiting, with an inclination of 60 degrees relative to the ecliptic plane. The sensitivity is in between this range, that is between 0.1 millihertz to 0.1 hertz, with the best sensitivity around 0.01 hertz, corresponding to 1/10 of an astronomical unit, and periods of days, hours, and minutes. Recall the LIGO Virgo are sources lasting fraction of a second, and you just scale with the mass of the object we are going to measure. The orbits of this spacecraft, it's optimized to minimize fluctuations in the vertices of this triangle, which is remain equilateral all over the orbit for about a lifetime of 10 years. After celestial mechanics cannot guarantee anymore the coherence of the shape of the triangle. The sensitivity of LISA is just plotted here. Here we have the strain sensitivity of the noise versus the frequency in the observer frame. And this is just the dashed line is showing the sensitivity of LISA. Sorry, not the dashed line, but the planned sensitivity is the green curve. But here you see a sort of reduction of the sensitivity, which is coming from a well-known galactic foreground coming from unresolved white dwarf and neutron star and black hole binaries. But we are mostly dominated by white dwarf binaries that by far are dominating the galactic population. that can not be solved better than this, and so that it is preventing us to, so we are losing some sensitivity here where I have the error, where I'm moving the arrow. The stars are the so-called verification binaries that are double neutron star, double white dwarfs that we see already in the optical and in the X-rays. And the little dots here are the white dwarf that we are expecting to detect as single sources that are monochromatic mostly. And so here we have simultaneously 10 to the 4th sources that are always there and that we have to extract in order to see the other sources. So the LISA data challenge is even more difficult than the one Einstein telescope has to face, but we have 20 years ahead. And let me talk about extreme mass ratio in spirals. This is in the frequency domain, the multiple frequencies at which we are going to see. This is the single signal that we see from an emery. What is an emery is, you might have heard about this, it is really a very nice system. So imagine you are at the center of a galaxy where there is a massive black hole similar to the Milky Way black hole, say of 10 to the 6 solar masses, just sitting at the center. We know from the observation by Gensel and Getz that there are stars around the black hole of our galactic center. We have 15 stars, well-determined orbit, very close to the galactic center, and we are going to, so this group are going to discover even fainter sources relatively nearby. And the idea is that we might have a stellar black hole, and before the discovering of the heavy stellar black hole, we were talking about black holes of 6 solar masses, but we could have also black hole of 40 solar masses. The one just 60 is a bit loose, but say 35 solar masses, 40, which is the mass of the black hole consistent with the existence of the inner edge of the pair instability, and so which is spiraling around very, very close. So this is a black hole on a very relativistic and highly generic orbit. The black hole has certainly a spin, and the object won't be orbiting in the equatorial plane. And this is a typical relativistic orbit that you can describe in general relativity. It is mildly, if it is mildly eccentric, this little black hole can cover 10 to the 4 up to 10 to the 5 orbital cycling before crossing the horizon. And people are now producing all the possible waveforms, which contains a lot of information. They contain the information on the spin of the massive black hole, on the eccentricity of the orbit, of the masses of both the big black hole and the small black hole. And the spin of the black hole, of the big black hole, due to the precession in plane and off plane, so the Schwarzschild and Lanthering precession, we can have exquisite measurement of the multipolar structure of a static space-time, not of emerging space-time, which is still vibrating, because you see the perturbations of the newly formed black hole. Here is purely static. So we might discover whether it is a curved black hole or not. We can test the Noether theorem. We can test if there are dark matter spikes around with precisions that are astonishingly large. So the challenge here is just to detect the signal that it is just where there is the maximum sensitivity, but there are a lot of sources around. But this is really peculiar of LISA. So MRIs are believed to be the best way to test the stationary structure of space-time to tell whether it is a curve or there are deviations. And this is an amazing science that we cannot do with Einstein telescope. Then there is the famous, ultra-famous suggestion by Alberto Cesana, which is in my institution, that as soon as the first black hole was discovered by the LIGO-Virgo collaboration, GW150914, of 36 plus 30 solar masses and more than 60%, 60 solar masses, the total mass. But here you see the in spiral signal that you can see years, 70 years, 6 years or months before it is entering the high frequency window of terrestrial interferometers. So this is the first and unique example of what we call the multi-band observations of stellar or intermediate mass black holes. So we see them in the LISA band, months of years, and we can tell it would be nice if it is months, so they have to be very nearby to say, oh, I'm discovering a double stellar black hole binary. I can tell you the chirp mass and the masses, and cannot tell you that in 6 months with an accuracy in the coalescence time of an hour or so, that it will enter the LISA, so the advanced LIGO bandwidth or the cosmic explorer. And so you can localize the source by exploiting the LISA motion, and you do fantastic physics if we succeed in having. The rate of this event is uncertain. We may have 5 or 100 of these sources, but this is something that's been discussed. And since we are now discovering the outlier with the mass of the 2 individual black holes in the pair instability gap, I think that with 04 and 05, we need to even revise the rates for these events. And then one of the most important targets for LISA is the discovery of the coalescence of massive black holes. So the analog of what we are doing on Earth, but with black holes of 10 to the 5, 10 to the 6, and 10 to the 7 solar masses. These black holes are located at redshift 3, have a mass ratio of 1/3, and this is the frequency signal, the amplitude of the signal in the frequency domain. So here is the chirp, so the rising frequency, and in the amplitude in the time domain, the peak is corresponding to the merger, and then you have the ring down. And so you see, I think here is maybe not, but months, weeks, and days and hours before the merger. And so this is fantastic. And in order to understand the horizons of LISA concerning binary black holes, here is the horizon we computed, and it is in the Astro PH paper. That is the paper that is describing the submission to LISA to the attention of the European Space Agency. And here is again the plot, the analog that I have shown for ET. It has the same meaning as this one. okay, as this one, that is going very, that is, we call it waterfall plot because it looked like a colorful cascade. We have the redshift here in linear scale. We have the mass of the binary, rest frame. The mass ratio is 1/3 for these binaries. And here we have the corresponding luminosity distance associated to the redshift. And here we see the lines of constant signal-to-noise ratio, 10, 20, 50, 100, 2000, 500, 1000, 3000, if the source is at very low redshift. This is the average because the sources, when we do this waterfall plot, the SNR is computed from a random distribution of angles in the sky, random polarization angles. And so this is really average and not the best sources located just on the top in the best location in the sky. So this is real average, okay? Which makes sense because we don't know whether we have so many sources to have the one just on the top, but they are on average distributed over regions of the sky where maybe the signal-to-noise ratio is low for the same set of intrinsic parameters. And you see that LISA is mostly sensitive to 10 to the 4 up to 10 to the 7 solar masses. And so out to redshift 20. So again, we are exploring the entire universe. And in particular, we are exploring by detecting the merger of the two black holes, we are indirectly detecting the merger of the galaxies in which they are hosted. So we are tracing the galaxy assembly, not by looking at galaxies as JWST will do, but by looking at the black holes that are hosting. And this is just a cartoon. So suppose you have a black hole which is forming at redshift 16. In a galaxy, there is another black hole that formed in a lower redshift galaxy with its dark matter halo. The black hole might also accrete, and so during this time scale, so it was born at 10 to the 4 solar masses, but it was accreting, and then it is encountering this black hole that accreted. There is a merger, you double the mass on average, and you see a gravitational wave transient of weeks, lasting weeks, and then the black hole will keep on growing and become a quasar at redshift 7, or a quasar that we see at the peak of the star formation rate, where there is also the peak of the AGN activity. So here I introduce two concepts. I can see the black hole as gravitational wave sources and as accreting sources, because accretion appears to be inevitable. Let me just, since it is already 8:10, we have the supermassive black holes, the stellar black holes, and here we have difficulties in detecting these black holes, because if they are accreting, they are dim, and if they are gravitational wave sources, the sensitivity both of ground-based and LISA is going down. But we can see the edges of this population. What we have learned about astrophysical black holes, let me just say it in the summary, and maybe I return to these plots later on. But I think in 5 minutes I'm over. So ease of observation of active galactic nuclei, that is accreting black holes, we discovered this five important facts. We have discovered the existence of AGN and QSOs that are powered by accretion onto supermassive black holes of million to billion solar masses. These are candidate black holes because QSOs, from the light curve, we can measure the masses, but certainly, and we see the light coming from a disk, an accretion disk, which is extending down to the innermost stable circular orbit. But a measure of the location of the innermost stable circular orbit, well, it's very difficult from the light to tell. We have discovered that the black hole masses measured with high accuracy in nearby galaxies, really in the zero redshift universe, correlate with the properties of the galaxy. That is, less massive black holes live in less massive galaxies. And this correlation is very important and surprising. For the reason is that the black hole is a tiny object. A 10 to the 6 solar mass black hole has a gravitational sphere of influence of comparable to the solar system size. And it knows to live in a galaxy where you have 10 to the 11 stars. How could a tiny object know that he's living in a galaxy with this given mass? And the reason is that when it was active, the energy that was injected by radiation or by the jet was self-regulating the star formation. And so when active, this correlation was established. Combining this information, I cannot tell the details, we have to combine this information with an independent information that when we look at the population of active galactic nuclei and the X-ray background that is pervading the universe and that we know is coming from unresolved AGN, we know that the bulk of these black holes was really the mass was built up due to radiatively efficient accretion. So it means that the black holes that we see in today's galaxies were born lighter and grow in mass by accretion. And also their spin was shaped by accretion. But we know that we are living in a universe where galaxies are forming from the cosmic web. And so then here is the picture. Black holes are growing by accretion because we have consistent, self-consistent and compelling observations in the electromagnetic universe, but we have a theory that is telling us that the galaxies are forming by mergers and by accreting baryons and dark matter. And so with LISA, we are probing the evolution of black holes that had to come from what we call light seeds. And the other important fact is that with deep observation, now we see black hole of 10 to the 9 solar masses. This is shocking. 10 to the 9 solar masses at redshift 7 during the epoch of cosmic reionization. So when the universe was less than 0.9 billion years old. How could such a monster be there in such a short time scale? It means that he had to merge and accrete from seed in a very rapid way, and it is very, very difficult to make it. So astronomers are telling us that supermassive black hole has to come to birth far lighter than what we see, both at high redshift and at low redshift. So they introduced the existence of the concept of seeds. So from now on, remind that we call black hole seeds the black holes that then has to grow to become the supermassive black holes, and that necessarily have intermediate masses. And then had to form at very high redshifts in high sigma density peaks of the dark matter halo under extreme conditions of low or null eccentricities. So seeds are transitional objects, almost single epoch star forming objects that are grown by accretion and merger. Accretion and merger that erase information about their birth properties. But LISA has the sensitivity, and let me go back here, to discover at redshift 10, say, or 12, black holes of intermediate mass, and understand if they were there, they could contribute to the growth of the supermassive black hole. And I'm spending time in understanding which are the seeds. And in 2 minutes, I would like to say that they could come from population 3 stars that we are going to see with Einstein telescope that are top heavy, so 100 solar masses beyond the pair instability gap that can exist because they are metal free. And remember, if you have a star which is metal free, it can be very massive because the Jeans mass is big and because there are no winds. Or the other prevailing but still unclear pathway is that you might have the direct collapse of a cloud of this size into a black hole. And in order for this cloud not to fragment and form stars, this cloud has to be irradiated by UV radiation in specific regions that are very rare. Or, I'm believing this is the real pathway, is that you have very dense nuclear star cluster and you grow very, very massive star by multiple collisions. And you can form by multiple collision, not black holes, but very huge supermassive stars that we don't see anymore, up to 3,000 solar masses. And then they grow by accretion and merger, accretion and merger. And this is a cartoon done by Metzger that is telling you all the possible pathway to explain the supermassive black hole. So we have hypotheses. They could come from black holes beyond the pair instability gap, or from stellar collisions, from direct collapse. And so maybe the unique seed, if it is coming from population 3 beyond the pair instability gap, only the little stars are always forming the big black holes. And this is absolutely fascinating to me because it is like the Lego. I don't know how to say in English, but when you construct with the Lego or the cathedral, you have a single building block, and then you assemble thousands of building blocks. And so maybe stellar collapse is just the physical process which is also leading to the supermassive black holes. And this is discussed in my Nature Review paper, and I think it is conceptually fascinating. And I'm finishing with this astonishing figure. We studied jointly in a cosmological framework the possibility that light seed or heavy seed, light seeds are the round dots and the triangles are heavy seeds that are, the light circles and light triangle are heavy seeds. Instead, triangle and circle describe different halos. So let me just go slowly 1 minute. Here I have the waterfall plot of Einstein telescope, sensitive to black holes between 10 and 10 to the 3. And then I have the LISA waterfall plot. And the nature is, these dots, you could see this as a statistical population of light seeds that are growing by mergers. These are merging light seeds that are growing by merger and accretion to account for a quasar at redshift 7. This is the triangle. The circles are light seeds that merge and grow to produce a quasar at redshift 2. So if we statistically combine observation with Einstein telescope independently, they are not time correlated, with the observation of LISA, we probably can tell whether you are dominated by seeds that are heavy or are light. And I'm finishing with the plot of my review showing that the power of Einstein telescope and LISA in understanding the origin is black hole is far better than all facilities that are going to discover intermediate mass black hole, but just below redshift 10, which should be sufficient. So I think that we need a complete sort of understanding of this. And but the power of gravitational wave astrophysics together will let us know the origins of the supermassive black hole. And maybe the only gravitational collapse in nature is that present in stars. And I stop here. Sorry, I was a bit too late.
Thank you, Professor Colpi. Okay, there are a few questions. Okay, I'll read the question in the chat first. So the question in the chat is, we can detect the IMBHs in the range of 1000 to 10,000, 10 power 4 with DESIGO, as it has sensitivity frequency band between LISA and ground wave detected?
Yes, the answer is DESIGO should be the third interferometer in space, a second, so an interferometer in space that is just covering this white region where both LISA and ET can make it. Notice that LISA can detect 10 to the 3, but at very low redshifts. That would be remarkable in any case. So the discovery of intermediate mass black hole at low redshift would be remarkable. And maybe we see at low redshift because there is always a time delay between the merger of the halo and the merger of the two black holes. Because with LISA, we have to wait the merger of the halo of the baryonic component, which are the galaxies, and then the black hole, through a sequence of dynamical processes that I couldn't describe. And also having black hole binaries of this order, we don't know whether they form. So it is highly speculative, but the DESIGO would be fantastic. And I know now, but I haven't had time to read, that there is the plan to conquer the moon again and use the moon as a laboratory. And they are thinking to seismic instrument that can detect gravitational wave just in the band also of the DESIGO. But the DESIGO should be done in the next future because it is fantastic. So it is it is covering what we can't cover, but it will be in the 50s.
Okay, Aditya, I have allowed, you can speak away.
Thanks, Chandra. My question was regarding one of the points in your slide where you said that lighter supermassive black holes are found in lighter galaxies, and
Yes.
consequently heavier ones in heavier galaxy. Is there a mass relation, like some sort of a exponent that tells us about this thing, a theoretical postulate or something like that?
Yes, yes. Let me go back to the slides I skipped. These are the relations you are talking about. The best relation, because it has less scatter, which is already huge, but for an astronomer, this is a very tight correlation because astronomy, you have many complex objects. So here you have the mass versus sigma relation. And I don't remember exactly, but the exponent, so the black hole mass is going as a constant times sigma to a power that could be in between 4 and 5. If it is 5, it means that the correlation is established because the black hole, when is active, is injecting radiation and thermal energy by the radiation, which is eating the interstellar medium and is quenching stellar activity, because you have driven the interstellar medium to a hot phase and you cannot cool it down efficiently. If it instead the exponent is 4, it is believed that is more that you are pushing away gas from the region of star formation because of momentum and winds. And the exponent, I think it is 4.2 plus an error, which I forgot which is telling you that probably there is a mixture of effects. So astronomers are finding that AGN are also not sources of immense luminosities, but also of very non-relativistic outflows, then are site of ultra-relativistic jets. So you are probably combining all these to make this relation possible.
Thanks.
Sasha?
Yeah, so thank you very much once again for a very nice set of lectures. So my question is pertaining to one of the slides where you mentioned that the merger of supermassive black holes are tracers of the mergers of galaxies. So I have two related questions. My first question is, can we envisage scenarios in which supermassive black holes can live isolated outside of galaxies and merge? Are there scenarios like that? And my second question is whether when you have the merger of these supermassive black holes within galaxies, are we guaranteed to have an electromagnetic counterpart because they live inside galaxies? So those are my two questions.
Okay, so very nice question again. So I'm really happy about your question, really excited about this. The first question is that if we see an off-center, so let me first say that the bulk, so 99% of the active galactic nuclei are always seen at the center of the galaxies, especially when we also, and even in our nearby universe, our black hole is just in the middle of the Milky Way, and it is there very, very slowly moving. I think that the motion of the galactic center black hole is less than a few 10 kilometers per second. So they are always deep in the potential well. So a black hole not to be in the potential well in nearby galaxy means that it is the outcome of a merger and it was recoiled. And thanks to the gravitational recoil, is not any longer in the center of the galaxy. We have one evidence, but it is really very rare, but it would be fantastic. There is a paper by Chiaberge that using double space telescope, he has claimed that you have a black hole that was ejected from the center. But this black hole, which is off center, could also come from a merger with a galaxy, which is just entering, and you see just the galaxy with an active black hole. So it's very important to see, to detect velocities, to see if it is outgoing or incoming, because the scenarios are very, very different. This is in the low redshift universe. In the high redshift universe, cosmological simulation that also we did with Marta Volonteri and Hugo Fizer, is that when in the high redshift universe, galaxies are not really well defined. You have halos with baryons, with stars, with morphology that are keep on changing. And if there are black holes, even the black holes that are formed heavy, they are never at the center. So to make a binary at high redshift, it might be difficult because they are randomly moving into a structure which is also randomly changing. So maybe the black hole of 10 to the 4 are at redshift 14, but we will never see them because they will never pair and coalesce at that redshift. And this is the large uncertainty. So when we will read off the data that will come from LISA, it will be very difficult to understand. Suppose we don't see, can we tell whether they are not there or there are no binaries? And so this is why we need probably to combine also with electromagnetic observations. So the message is merger can eject black hole. If there are in voids or in low density region, we will never see them. There are models in which they say also that if you have a galaxy, which is the outcome of many, many also minor merger, even in our Milky Way, we might have wandering black hole of 10 to the 4, 10 to the 5 in the halo of the Milky Way. Okay. Or maybe one which is coming close and we don't see it. But we don't see local perturbation in the sky. But it would be fantastic if Gaia would see some anomalous dynamics of stars associated to a massive perturber. Concerning to the second question, indeed, there is a lot of discussion that it is quite likely that you see a merger in LISA. There is a lot of gas at the center of galaxies, not in our galactic center anyway. And we are working, personally, I am working on electromagnetic counterparts. I can tell you that LISA, despite the orbital motion, it will be able to see counterpart out of merger out of redshift 2 or 3, not anymore, or not farther away. But if we are able to, and we have not yet understand what would be the electromagnetic signature of a merger, not in spiral, because we know the electromagnetic signature of the spiral, but it is very difficult to see the spiral, then we can do and measure the Hubble constant as we do with neutron stars. And the answer is, it is likely that many merger will come in gas-rich environment, that they are not corrupting the waveform, but they can create a counterpart. But it is open questions, and we need to really do a lot of investigations.
I see. So if I could just ask a very short, quick question in follow-up to this, I was just wondering whether the fact of seeing or not seeing a counterpart could actually tell you something about the nature of these mergers. Maybe they're formed in different scenarios, or maybe the supermassive black holes don't live at the center of galaxies or something like that.
Yes. Let me tell you, when we are talking about 10 to the 9 solar mass black holes, these are in elliptical galaxies. They can merge in galaxy cluster, but these are not visible for LISA because, as you can see, 10 to the 9 is away from the sensitivity of LISA. And PTA can see them in spiral. And, but the foreground and maybe individual, if you see an individual source, you may discover this. The black hole of LISA are 10 to the 6 that in today galaxies are in disky galaxies, are in the bulges. But certainly if you don't see a counterpart and you are sure that you have seen the galaxy, it's because it was a dry merger. And again, it would be again very important because then you see that it is sort of occurring without being the dynamical hardening of the binary was not controlled by gas, but by star. And so we learn a lot about the dynamics of the merging systems.
I see. Thank you very much.
Thank you, Sashwat. Are there any other questions? Okay, there doesn't seem to be any other questions. Okay, there seems to be something in the chat, but I think, okay, I think it's a thanking, it's a message thanking you, Professor Colpi, for the lecture. All right, if
I couldn't hear you anymore. I couldn't, do you hear me?
Yes, yes, Professor Colpi. I think you're audible. I
Okay.
think Chandra, there seems to be some issue with audio. So
Don't
Chandra, you
worry.
could probably type in the chat box what you wanted to just conclude the session, because you are not audible, Chandra.
Personally, I really, if you can hear me, I really want to thank you for being also so patient to listen to my lectures, but I also enjoyed your questions. And so it would be nice, I was thinking that it would be nice if we could really so meet again with these Indian postdocs, because it would be very great to exchange ideas and projects. So I really thank you for maybe I excuse myself that my first lecture was even too simple, but I didn't know your experience, but really it was a very good experience also for me.
Thank you very much, Professor Colpi. I think they were a really helpful and wonderful set of lectures.